talking about titration curves and drawing the particulate models along the titration curve because they make a big deal about this. This is something they like to see, and this is good particulate model counting and mole counting to make sure you're reading the diagrams correctly. I do like this graph that I found that's on the front slide here, just to kind of recap a few things for you. As you can see in the pink here, this is the strong acid, strong base curve. One thing you should notice about it is it starts lower on the pH scale. The strong acid, strong base is lower. It's also a little bit flatter across here, okay? And you have the larger inflection going up like so. Also, you would notice that right here at 7, pH 7 is where the equivalence point would be in the middle of that inflection right there, okay? Now, the weak one right here starts higher up on the pH, okay? It's going to start up a little bit higher because it's not as strong. And we also have this buffer region. It's a little bit more of a slope. So this is the buffer region. Don't forget, buffer region. Okay, where in the midpoint of the buffer region, the pH equals the pKa. Why is that? If you did your notes, you would have seen the Henderson-Hasselbalch equation. The pH equals the pKa plus the log of the base over the acid, like so, right? Everybody remember this equation? Seen it? The Henderson-Hasselbalch equation? Well, if you haven't, this is the equation, but taking a look here, the midpoint of the buffer region, pH equals the pKa, that means that the acid and the base, their concentrations are equal. Let me rewrite that, or it's a little funky. These concentrations are equal because that means this turns into the log of 1. And what is the log of 1? The log of 1 is 0. So this part of the equation wipes out. So what's left? The pH equals the pKa. So at the midpoint of the buffer region, right there, your concentration of your acid, your weak acid, equals the concentration of your conjugate base right here. So kind of pay attention to that, because if you're before the midpoint, you'll notice a trend. If you're after the midpoint in the buffer region, you'll notice a trend. But I like how this kind of distinguishes the main features that are different between the weak acid, strong base, and the strong acid, strong base curves. Sometimes they ask you to compare and contrast them, just so you know. All right, so we're going to start with the strong base, strong acid one. As you can see, we're starting up here, the higher pH. We're going to be adding acid as we go, HCl. Adding acid to the strong base. The strong base happens to be sodium hydroxide. We're titrating it with HCl. These nice, easy, monoprotic acid with its, it's just one hydroxide per formula unit here. We're going to use these different symbols over here to draw, or you can create your own, but usually they designate, you've seen where you've had to draw them, they tell you what they want the shape and stuff to look like to represent the different molecule or atom that you're dealing with. So here, what you'll see, as you're going along the titration curve, there's a few data points that they want you to represent. How would it look? What are the most prevalent chemical species? The ones that are in there in high concentration. They don't want anything that's minuscule, and they definitely don't want you to have to represent water, because water's in there in a huge abundance. So here, starting at the top here, for A on our curve, as you can see, they've already represented it here. And usually they do. They give you a starting point so you can count your molecules and know what you're starting with. So if we go ahead and do that count here, okay, this 0.10 NaOH, really what are we seeing here? We're seeing 1, 2, 3, 4, 5, 6. 6 of our NAs, and then 1, 2, 3, 4, 5, 6 of our OHs, okay? So that's representing the 0.1 sodium hydroxide, 6 and 6. All right, nothing's been added there. No acid yet has been added. Now, if you look here at part B, okay? Part B, some of the acid has been added. Because we're right here, at B, this is 12.5 milliliters, right there, that's been added. So it's sort of like the halfway to the equivalence, even though there is no midpoint, because these guys don't have a buffer region. Remember, the sodium is a cation of a strong base, so it is neutral. And then if you look at what we're adding the acid, HCl, okay? HCl here. So this is going to be the anion of the strong acid. So it's also neutral. So that's why we don't have a buffer region. We don't have any weak acid or weak base conjugates in there. Now another thing I want you to consider here is this is strong, strong. We need to know our net ionic equation for strong. So the net ionic, remember this would be the H plus the OH minus. That's going to give you 1 water. Okay? This is how we're going to be able to keep track of how much should be in there, right? So if this is representing 0.1 before we've even added anything, 6 and 6. Now we've gotten halfway to our equivalence point. How much has been neutralized? How many of the OHs have now combined with an H to form water? 3, thank you. Really, it is that obvious. Yes, we're going for obvious here. So we have now neutralized 3 of the hydroxides. So if we're at that halfway point, we should have added 3 here, there's 6 here. So that means there should be 3 hydroxides left, okay? So I'm going to draw in the hydroxides here. They like the dots. There should be 3 of them in here. All right, now, my question is to you, we had 6 of the sodium to begin with. Does anything happen to the sodium? Do they react with anything? Do they do anything? That would be a no. So they are still hanging around. All 6 of them, they have not done anything. They're still in solution. They're still here in their ion form. So we would need to draw in our 6 sodiums, right? Like so. Now the other thing to consider is there's one other chemical species ion that's floating around in there. What is it? Who can tell me what it is? There's one other thing in there. Yes, it is the chloride. Because if you think about it, if you added 3 of the H's, that means we have to have how many chlorides in there? We would have to have 3 because for every one of these, we would have 3 Cls. Now I'm going to use blue for the Cl. So, like so, because I can't really shade mine gray. The 3 hydrogens, remember, neutralized the 3 hydroxides and formed the water. So those aren't in there. Okay, so the 3, we know 3 were added because we start over here with 6, right? 6 hydroxides. And if you look here, we're at 12.5. So we got halfway because the equivalence point is at 25 milliliters right here. So we've gone halfway. So we know that half of the hydroxide should be gone. So half of the 6 means 3. And that's why we know 3 H's, would have been added in there. Does that make sense? Okay, good. So we got to B. Now let's look at getting to the equivalence point. All right. We're here at the equivalence point. What is the definition of the equivalence point? We're at C now. Right here on our curve. What do we know is equal at the equivalence point? What's equal at the equivalence point? Yes, the moles of the hydroxide, the moles of the hydrogen. They have all now combined and formed water. Remember our net ionic. Don't forget that. It's the H plus the OH. Right now, at the equivalence point, now all we have is water. We don't have either of these. They have now neutralized out. So really, in essence, what are the only things in there at the equivalence point still floating around? The Na and the Cl. Now, we know we had 6 NAs to start with. The NAs have not been added or removed. So we're going to have 6 more NAs in here, like so. But at this point, how many chlorides should be in there floating around? How many H's had to be added to get to that equivalence point? How many hydroxides did we start with? We started with 6 hydroxides, so we needed 6 H's to get to that equivalence point. So that means how many chlorides are in there? 6. Good. And remember, I'm using blue for the chloride because I can't shade mine in the gray. 1, 2, 3, 4, 5, 6. There we go. Exactly right. Now, all this stuff that's in here at the equivalence point, that's going to stay in there, right? Because when we get to D over here, we're just adding a little bit more acid. We're going to keep adding some acid there into that point. All right? So all of this stuff that's in there at the equivalence point is still there, the sodium and the chloride, 6 and 6. So I'm going to go ahead and redraw them over here. 6 sodiums, floating around, having a good old time. In between the waters, spectating, remember. They don't react with anything because they're neutral. That was from A. I got the 6 hydroxides and 6 Na because that's what they originally told us were in there to represent the 0.1. Okay, no, that's fine. It's good to keep track. Where are we getting these numbers from? Totally good. And it gets confusing with all the circles. So yeah, clarifying is fine. All right, at this point though, we've added a little bit of extra acid. Not like completely to where it's like another 12.5, where you would add 3 of everything, right? It's a little bit before then. So I'm just gonna add two more HCl's in there since we've added a little bit extra. I'm gonna use green for my hydrogen. So I'm adding in 2 hydrogens because we have now added some more acid, and that's why it's starting to, the pH is going down at that point. Because we've added a little bit more acid. But that means, remember HCl, when it breaks apart, you get H plus and Cl minus. So we have to add a couple more of these. Because we add 2 of those, that means 2 of those are in there. So we actually have 2 more of our chlorides in there. We don't do any water, we don't draw any water because water is super abundant. So we already know that's in there and super abundant. So here we're only representing the ion species in there. That is exactly right. So this one actually is the super easy one because you're about to see the weak acid strong base curve. And there's more points on it. Now we're not going to get that far in here, but as you can see, they like to have you look at, yes, of course, the before and the after and the equivalence point. Those are pretty typical. But now we got this buffer region to contend with. We know the midpoint of the buffer region is C. And then we have before the midpoint and we have after the midpoint of the buffer region to deal with. And we're also going to be dealing with our weak acid with our strong base. So it's good to go back over the net ionic here. We've got acetic acid. Acetic acid is going to react with the hydroxide. Okay? And that's going to make some water. But it's also going to leave us some acetate floating around, the conjugate base, like so. Now for our purposes, you know, the H is taken off by the hydroxide. That's what forms the water. Then we're left with our acetate. I'm just gonna use the symbol HA to represent acetic acid because it's a super long formula. And I'm gonna use A minus to represent acetate when we get back into drawing these next class. But definitely take a look at them. You can also take a look at the titration practice, just like the one we did in the notes with different numbers. You can try to do that one or take a look at it. We will be working that on Friday, next class, as well as doing a few more buffer problems with the Hendy-Haas equation.